Evaluate the following arithmetic, leaving the answer in octal number system. So that is very important. The last part is very important. We have to leave the answer in octal equivalent. So let's start with the Roman 1. Roman 1 is binary subtraction because it is they are base 2 numbers. So we have 1, 1, 1, then we have 0, 1, 1, we have 0, 0. So we have 1, 3 ones, then 0, 1, 1, then 2 zeros. Then this is subtracted to 1, 0, 1. Then we have 1, 1, 0. And we have 0, 0. So this is binary subtraction. And you have to know the rules of every arithmetic, be it addition, subtraction, multiplication, or division. So for binary subtraction, we normally say 1 minus 1 is 0. 0 minus 1, this is impossible, so we have to borrow. We borrow a 1 from the next column. Then 1 minus 0, we normally get 1. And 0 minus 0, we get 0. So you have to know the rules. So here we are going to use the rules of binary subtraction. But what we get, we change to octal to get the final answer. So 0 minus 0, we get 0. Here we get 0. 1 minus 0, we get 1. We get 0. 0 minus 1, we borrow 1 from here. We remain with the 0. When we bring it here, it becomes 1, 0, which is equivalent to 2. And when we subtract, we get 1. Here we remain with 0, so we borrow again from here. We remain with 0. We get 1, 0, which is equivalent to 2. We get 1. 0 minus 0, we get 0. And lastly, we get 0. So this is the number that we are getting, but we have to change it to octal. And from binary to octal, what you should know, we normally represent octal numbers in binary form using groups of 3 bits. So what you do, you take your number, and you divide in the groups of 3 bits from right to left. So in this case, the first group is up to that point. The second group is up to that point. And when the last group does not have 3 bits, you add 0 to the left to make 3 bits. Then after you do that, for every group, you write the equivalent octal number. So here we get 0. This is 6, and this is 4. So in this case, this 0 is does not have any significant value. So in this case, we get 64 base 8. That becomes the answer for that Roman 1. We go to Roman 2. Roman 2, as you can see, we have a base 16 number and a base 8 number, which cannot be computed like that. So we have to change, because the final answer should be in octal. It is good to convert the base 16 to octal. Then we perform the addition. So we shall first convert our BC base 16 to octal. And from in this kind of a conversion, we don't have a direct method from base 16 to base 8. So you can either change to decimal and then back to octal, or change to binary and then to octal. But the simplest way is from base 16 to binary and then from binary to octal, the way we have seen in this case. So base 16 to binary, what you have to know again is that we write base 16 numbers using 4 bits instead of 3. Now we use 4 bits, and in base 16 we represent the numbers in base 16 from 0 to 9. We represent using the normal numbering, but from 10 to 15, from 9 next will be 10, but in hexadecimal we don't write 10, we start with A, then B, C, D, E up to F, where F is 15. So in hexadecimal from 10 we start with A. So in this case, what we do to convert base 16 to binary, every digit we write it in 4 bits. So B is equivalent to 11, and 11 is normally 1011. If you cannot remember this value, using this table, if you know it is 11, you can use the normal method, which is 11 you divide repeatedly by 2, writing the remainders on the other side, and you will be able to get this value. Then C stands for 12 when we follow the numbering. So if you don't know the value of 12, use the method of division by 2 to get the binary. But in this case, C is 1100. So our number in binary is 10111100. So that is our binary number. Then this binary number, now we change it to octal so that it can match with 57 base 8. So now we group it in 3 bits because we are going back to octal. So we shall group in groups of 3. So the first group is that, the second one, the third one has got 2 digits. We add 0 to the left to make 3, and for every group we write the equivalent equivalent octal number, and this one will give us 274 base 8. So we take 274, we add 57, we get 274, we add 57. So this is octal addition. So octal addition, so any number which is above 8 you have to carry, and also if it is 8, if the sum is 8, we also have to carry 1. So always you carry 1. So for example, 4 plus 7, we get 11, and the 11 can be written like 1 times 8 plus 3. So this becomes the carry, and this becomes the sum. So the sum you write here, and you carry 1. So the same way we add normal numbers, when we get any number which is either 10 or above 10, you write the sum and you carry 1. So here we always carry 1 if the number is above or 8, is above 8 or is 8. So in the next column we have 1 plus 7 plus 5, which is 13. 13 can be written as 1 times 8 plus 5. So 5 is the sum, so we write 5 and we carry 1, which is here. and the last one is 1 plus 2, which is 3. So in this case, our answer becomes 353 base 8. Or else, if you don't write like this, you can just take whatever you have gotten, if it is above 8, and you minus 8. For example, this is 13. 13, we subtract 8, we get 5. And the 5 goes here, and we carry 1. Suppose we were getting 8. We could have taken 8 minus 8, which is 0. And we write 0, we carry 1. So we don't write 8 if we get 8. We write 0, carry 1. This is because, for example, when you take 55 plus 65, and we are using the normal addition that we know, 5 plus 5, when we get 10, we don't write the 10. We write 0 and we carry 1. So the same way, if it is base 8, when we get 8, we write 0, carry 1. Because the normal addition that we know is normally in base 10. So when we get the 10, we don't write the 10, but 0, carry 1. So that is how we do those two.